Yeah, what's up? It's Coach Hyde. Got a high science video for you right here to follow up on our introduction to acids and bases today, where we did the taste test. We tested several different substances, and we came to the conclusion that acids taste sour, and that bases taste bitter. We tasted several different things. We tasted the acids we tasted were lemon juice, pickle juice, vinegar. I think that might be it. Maybe some soda. So we got some carbonic acid, some citric acid, some things like this. It gave us a sour taste. The bases we taste were 100% pure chocolate to give us that very bitter taste. We also tasted some baking soda. It also gave us a bitter taste. So going a little bit more in depth with it this time, kind of taking it a little further. So we talked about the taste. Next thing is to look at the chemical composition of acids and bases. Really kind of dive in there and see what is it that makes it an acid, what is it that makes it a base. These are a couple examples of some strong acids. We got hydrochloric acid, nitric acid, phosphoric acid, and hydroiodic acid. And one thing that they all have in common is this hydrogen up front. This is the hydrogen ion that makes acids acids. If you remember our discussion about the hydrogen ion, which is when we said, let's just look at a hydrogen atom. Okay, so a hydrogen atom has one proton, 0 neutrons, and 1 electron. All right, we make the hydrogen ion by stripping away the electron. So really, all right, there's no neutrons. So really, a hydrogen ion is just a proton. So an acid is kind of defined as its ability to give a proton. Well, that's all it is a proton. So that's what acid is, the giving of the proton, right? Now looking at the bases, there's a couple of the strong bases. What do they have in common? Now this one, I'll write the name out for this one. I probably will spell it wrong, but this is the hydroxide ion. So this is similar to the acid is the proton, the hydrogen. This ion that we associate with being basic or alkaline is the hydroxide. So that is at its base what the acid is and what the base is, especially when we come up with water. So looking at how we put this on the scale, right? We look at the pH scale. So just like we use grams for mass, meters for distance, hertz for frequency, we always have this unit to measure things. If you've noticed that as we moved on through here. Well, pH, right? pH is our unit of measurement that we will be using for acids and bases for us. So on this scale, this number tells us if it's acidic or basic. In the middle here, this giant 7 is neutral. Okay? This doesn't mean anything. It doesn't mean that something that is neutral is weak. It doesn't mean something that is neutral is strong. All it means is when it's neutral is that, hey, this is not an acid and this is not a base. Okay? It could be several different things. It could be mineral spirits, it could be acetone, it could be alcohol, it could be water. It could be a numerous different substances. It's just saying, hey, at 7, it's not acidic and it's not basic or alkaline. All right, over here on this side, these numbers represent acids. These numbers represent bases. Now, how we figure out these numbers, if you remember, we will count all of these hydrogen ions and we'll put them into a logarithmic equation with a base of 10, right? And we will solve it. You'll learn how to do this later on in chemistry and actually set the equation up. It's really quite simple. But when we work this out, it gives us a number 0 through 14, and that is our pH. So it's based on how many of these hydrogen ions there are. If there's a lot of them, if it's a really strong acid and there's tons and tons, highly concentrated H positives, then we would be down here in what we call the strong acid, right? If there's not many of them, but still acidic, right, then the less we have, the weaker it becomes. So this range, as we get closer to 7, is our weak zone, our weak acid zone. And on the other side, kind of the number's closer to 7, right? So, down here, all of these, this is going to be where our weak bases are. Out here is going to be where our strong bases are. So the further away from being neutral, right? We're neutral in here. The further away from being neutral, the stronger we are, whether we're talking about acids or bases. All right, so got through that. Now, last thing is indicators. We use a couple different indicators in here, right? Well, really only two. We use litmus paper. We got red litmus paper, blue litmus paper, right? We use these. Hydroxide paper. So you'll notice if you look at this on this scale here, we have like a color key, right? Whereas on these, there's no color key. So these are more general, like yes, an acid, or yes, a base. Whereas this one's like we can tell you spot on if it's a strong acid or a weak acid, strong base or weak base. I'm gonna show you a couple examples of that. So first, let's look at red litmus paper. Right now, if you haven't figured it out yet, red is used all the time for acids. Blue is used all the time for bases. So let's see what happens using these red and blue. So up first, blue litmus paper, right? Straight blue. This is HCl, hydrochloric acid. Not that. I don't know where that's from. All right, this is hydrochloric acid. So if I put my blue litmus paper in here, let's see what happens. It turned red. Wow, that's it. It can change color, or it doesn't, right? So what about I put it into the base? Turn back blue. You see the little difference? Pretty cool, right? So, if I started with one that was already blue and I put it into a base, this is sodium hydroxide, by the way, it's just going to stay blue. So all this litmus paper that's blue does is it can turn red in the presence of an acid, or it just stays blue or turns back blue in the presence of a base. What about red litmus paper? Okay, so again, this is sodium hydroxide, it's a base. I'm going to put red litmus paper into the base. Surprise, surprise, turn blue, right? Well, what if I put red litmus paper in an acid? So it didn't work quite as good. Got saturated. There it goes. So turn back red, right? If I started with it already red in hydrochloric acid, it would stay red. So our litmus papers, they either stay the color they are. So blue will stay blue if you put it in a base, but it'll turn red if you put it in acid. Red will stay red if you put it in acid, or it will turn blue if you put it in a base. Now, if we want to be more specific than that, hydroxide ion, right? Now we have the color key, right? We can use the color key to get a little more specific, because maybe it's not just going to turn red or blue all the time. So if we start with our strong acid, hydrochloric acid, right? I dipped this in there. You bet turned red. Acid will never let you down being red. So I will compare this, right, to my key, right? This falls in right there, right? See how that color matches? Can we get up here? See how that color matches? This has a pH of 1. This is a very strong acid, right? So I'm going to move this way. We're going to grab another substance. This here, what is this? Never smelled like that, but I knew this was pickle juice, and it's delicious. So anyway, hydroxide paper into the pickle juice. Now, this is not quite as dark of a red color, so I put it on here. Let me see what we're going to be, right? Put it on here and compare it, right? It's lighter than that, lighter than that, lighter than that. Wait, right here? Right here? Looking at the camera, it's hard to see. This is a pH of 5. So this is a much weaker acid than the hydrochloric acid. Hydrochloric acid had a pH of 1, closer to strong. This one had pH of there. All right, let's grab this. All right, so we're going to take the pH of this. This is baking soda and water. There you go. So, baking soda and water in. Oh, green. So this is not red or blue. We'll see if we can find the green. So just kind of got a little flaccid on me there. So put it here. So green. So what green tells us, right, is it has a pH of, it might even be, maybe a little greener than 8, maybe somewhere like 8.5, maybe, you know, but so you see, it doesn't have to be. It can be anywhere on this range. And then finally, we'll go back to our sodium hydroxide, which was our strong base. We got a very dark blue color here, right? We match it up. It's got a pH of at least 12, so this is a very strong base. So here we've used indicators. We've studied, is it just going to tell if it's yes, it's acid or base? That's going to be our litmus paper. And then we can use this Hydroxide paper here, right, to see several different colors. I ain't going to pick them all up, but you get the picture, to give us a wider range of what we see, more specific pH value. So talked about, basic properties of acid bases, talked about the ions, hydrogen ion for acid, hydroxide ions for bases, talked about their taste. Acids taste sour, bases taste bitter. We have talked in the past about corrosiveness, which means it will damage or destroy whatever it touches, and a base can be just as corrosive as an acid, right? Especially depending on what materials. Now, acids tend to be corrosive to metals and release hydrogen gas, and bases tend to be a little more corrosive towards the organic stuff, but could be just as corrosive with one another. And then they're both electrolytes. Don't forget about that. So if you have an acid and a base in solution, that solution can produce electricity or conduct electricity. Sorry. Then we talked about our indicators, our red litmus paper, blue litmus paper, hydroxide paper, and we talked about our pH ranges, where we have the weak acids and bases, strong acids, strong bases. All right. Let me know if you need anything else. Catch y'all next time.